Thank you for attending the second talk of this plenary session today. Let me introduce Renée James. Renée James founded Ampere Computing in 2017, where she is currently the chairman and CEO. Ampere produces high-performance microprocessors for cloud and edge computing. Mrs. James had a lengthy career at Intel, where she served as president of Intel until her departure in 2016. During her tenure with Intel, she was the first female general manager of a business unit, as well as the first woman executive vice president that led R&D and global manufacturing operations. Mrs. James was also chief of staff to Intel founder Andy Grove midway through her career for over 4 years. James has vast global operating experience in both hardware and software development and manufacturing of semiconductors. She has led several development sites around the globe as well as directed the government affairs in those regions. She's an active voice for diversity and representation in technology, as well as the future of the US semiconductor industry. James was on the Fast Company list of 100 most creative people in business, ranked 21st on Fortune's most powerful women in business, and has been recognized on the Forbes 100 most powerful women list. Renée James is a member of the board of directors of Citicorp and Oracle. James has been a member of the National Security Advisory Committee to the President by presidential appointment since 2011 and is the most recent Chairman Emeritus. Thank you so much, Renée, for giving this talk today, and thanks everyone for attending.
Thank you, and welcome to ISSCC 2022. I'm sorry we're not meeting in San Francisco, but in these times it's important to be safe and healthy. I'm very happy to speak to you virtually from the cloud. I'm Renée James. I'm the CEO and founder of Ampere Computing, and I'm thrilled to have been asked to speak in a plenary session on such an important topic facing the semiconductor industry, the future of high-performance semiconductor design. I've been in the semiconductor industry for over 3 decades, all of it in design, development, and deployment of high-performance microprocessors. 4 years ago, I founded a new company, a design company, focused on the building of the future of high-performance microprocessors for the cloud and cloud edge servers. So the question is, why would someone decide to build a CPU design company focused on high performance? Isn't that business done? Doesn't one architecture already have 98% share? Why, Renée, would you do such a thing? And the answer is because the future will not be like the past. We need a new platform as we enter the build out of the cloud and the edge further into our everyday lives. We need something new for the new phase of computing, and the design must change as the market requirements and the demands have changed with the pervasive build out of the cloud. Computing really evolved in a linear fashion since mainframes, through mini computers to PCs, and then the use of PC technology in servers for client server and enterprise compute. And now we're in the era of cloud compute. And like the phases of compute that came before it, the demands have changed and a new platform is needed to address the future growth and needs. How do we know we're in a new phase of compute? We know because the underlying software approach has changed. The tools have changed, the way we build software, the way software is distributed, and how it's consumed through the cloud is fundamentally different than in the era of client-server compute. One of the hallmarks of a new phase of compute is you use the technology that's available to you to build the new emerging environment, and that's exactly what we've been doing in the cloud today. The industry has taken the x86 architecture and the approach pioneered over 40 years ago for the building of the PCAT architecture and applying it to cloud compute and the modern data center rack. I think we as a design community and as an industry can and must do better. And that is what Ampere is about. It's our mission to invent and deliver the new standard in design for cloud and edge servers with high performance and power efficiency, delivering a better total cost of ownership. Because if we continue to deploy old technology for new problems, we end up with a real problem in the consumption of power and the overall footprint of these data centers. So the semiconductor industry needs to deliver sustainable solutions that reduce the carbon footprint. For example, the cloud data center market is expected to double in the next few years. This is going to require a significant amount of compute resources. If the data center providers continue to deploy legacy solutions, they will consume 2 times the power and 60% more real estate than what's being consumed today. On the other hand, if they use cloud-native solutions like the ones designed by Ampere, they can deliver similar performance, if not even better performance, at a fraction of the power and real estate footprint. We're a 4-year-old cloud-native semiconductor global startup that is dedicated to delivering what comes next in the semiconductor industry for high-performance cloud compute. We design custom-designed cores and processors that are manufactured by TSMC. In the past 2 years, we've delivered the very first cloud-native 80-core Ultra and 128-core Ultra Max. In 2022, we will introduce the next generation of Ampere processors, which will be based on our own ARM-compliant cores. For the rest of the video, a few members of the Ampere team will help me discuss what's required to design for the modern cloud, what design challenges teams face, and what some of the techniques and approaches are that we've used to overcome some of the most serious design challenges facing silicon developers in the era of high performance and power efficiency. Let's start with what's really required from the silicon in the cloud market in order to be competitive. The demands of the customers in the market have changed over the course of the last decade. And as a result, the design point for high performance has moved as well. To help me discuss this further, I've asked Ampere's Chief Product Officer, Jeff Wittick, to give you an overview of the cloud market expectations. Over to you, Jeff.
Thanks, Renee. The major reason we've seen this move to a cloud compute model is that services can be seamlessly deployed and scaled across a vast hardware infrastructure. This ability to scale out in an elastic manner fuels the continuing growth of the cloud. After adopting a cloud environment, by breaking applications down into microservices, developers can more rapidly build applications with a higher degree of innovation. Because microservices remove dependencies between the parts, they can also easily scale individual components of the application to meet changing user demand. For instance, in an application like ride-hailing, there can be thousands of individual microservices running, which provide everything from matching the rider and driver, to mapping the ride, to billing when the ride is completed. These must scale based both on the complexity of an individual ride and on the number of concurrent rides occurring. When building the overall service, you want the rider's requests to complete as quickly as possible every single time. You need to be able to scale up and down with the number of riders, and you'd like to do so within an existing data center footprint at the lowest possible energy consumption. Increasingly, artificial intelligence has improved services further by adding incremental features like better route guidance and traffic intelligence. Much of the AI inferencing for these tasks is occurring at the edge in order to deliver the lowest possible latency. Lastly, as autonomous vehicle fleets become a reality, compute requirements will increase even further, and the need for low latency and high performance will become even more important, especially for critical areas like safety. While the cloud in general will double in size by 2025, artificial intelligence, especially inference, will grow even faster, over 5 times. If a sustainable approach to cloud infrastructure is important, efficient AI inference is even more so. Also, as cloud infrastructure becomes more distributed and less centralized to meet critical low latency requirements, having a power-efficient processor that can fit into more constrained power and thermal envelopes at the edge while still delivering high compute performance is a top requirement. Clearly, it is critical that the underlying hardware enables the desired elasticity, resiliency, automation, and portability required by cloud service providers and cloud-native developers. For this, you need the right type of CPU, one that delivers predictable high performance. This allows clouds to deliver industry-leading performance all the time to their users without worrying about degraded service. Platform scalability. This allows clouds to scale performance to meet increasing demand, as well as to scale out to more constrained edge locations. And power-efficient compute density. This allows clouds to deploy more capacity in the same power and data center footprint, leading to a sustainable and responsible solution. Now, I'll pass it back to Renée.
Thank you, Jeff. As you heard from Jeff, the considerations for the design point are more complex, with several variables at play. Many of them are conflicting on the design. So now let's move to a discussion of the key architectural requirements of these modern high-performance devices. It's by understanding the history of how we've built high performance and the challenges we have faced at each stage that we consider the new set of challenges of cloud-native processors and the balance between performance, features, and power. To discuss this in more detail, I'm going to turn it to Atik Bajwa, Ampere's Chief Technology Officer, and some members of the actual design team at Ampere to talk about what challenges they faced and some of the things that they have done. Over to you, Atik.
Thanks, Renée. As you heard from Renée and Jeff, the cloud has emerged as a dominant paradigm for the next era of compute. It is where the bulk of computation will happen in the future. And to best serve this new paradigm, we must develop products and technologies that are purpose-built for the cloud and optimized for the workloads that run there, not just repurposed legacy solutions from bygone eras. Speaking of bygone eras, a lot has changed over the 4 decades that I've been building high-performance processors. Back in the day, we could rely on the metronomic cadence of Moore's law, with each silicon generation delivering better density, allowing us to pack more transistors into a piece of silicon, faster transistors, enabling circuits to run faster, and smaller feature sizes, enabling circuits to consume less power. Power was a second-order consideration, primarily as a constraint on performance. Power efficiency and considerations of sustainability, climate change, and implication for the planet were not a major consideration in product design. On the performance front, the focus tended to be on peak performance for individual workloads that were themselves typically composed of large, monolithic software applications. In contrast, today, the challenging physics of atom-scale geometries have slowed the pace of silicon process improvements, both the cadence and across-the-board gen-to-gen improvements in density, performance, and power. Moreover, the increasing complexity of process design rules, coupled with a growing size of designs, means that exponentially more human effort and machine time is required to harvest the benefits of process improvements. Meeting the performance and functionality needs of today's cloud data center increasingly requires that we assemble multiple pieces of silicon together in a package. Performance means consistent performance under load with multiple independent and potentially interfering workloads all running on a single server. Power efficiency is a first-order goal, not just because of its impact on performance and total cost of ownership, but also because of its implications on sustainability. And finally, the software landscape is also quite different, with workloads increasingly composed of collections of software packages and an array of microservices, deployed in VMs or containers, with multi-tenancy the norm. So, with all that has changed, what does it mean to build cloud-native products? Well, it requires a clean slate approach to both what you build, the architecture of the product, and how you build it. Let me start with the what. High performance is obviously a requirement in the cloud, but just as importantly, cloud needs consistent, predictable performance, even under load. And given its multi-tenant nature, it is critical to prevent information leakage between workloads of different customers that are running on the same processor. The architecture must therefore provide dedicated hardware for performance consistency and for security isolation. Consistent performance also requires that the product be built to operate at a consistent frequency and not hop around between different frequencies depending on what else is running around it. Performance and performance consistency also require a cache hierarchy and memory subsystem that delivers high and consistent bandwidth to feed the CPU cores at scale and even under high loads. Using an architecture built for the cloud, cloud-native processors can deliver high, consistent, and predictable performance under load. Let's switch now to how to build cloud-native high-performance processors. I'd like to invite Mitrajit, who leads our silicon engineering team, and Yesh, who leads our advanced circuits team, to discuss some of the key implementation challenges in building these advanced cloud-native designs and how we at Ampere are addressing them.
Thank you. Developing the cloud-native server designs, as Atik mentioned, requires a holistic approach that optimizes across multiple design domains. And each domain requires a new paradigm in execution and implementation. First, the cloud-native servers require very large-scale integration combined with first silicon success and high-volume manufacturing. Second, the performance and power consumption must continually improve to keep pace with demand. This performance also pushes the need for higher I/O bandwidth, which is making an impact today. With the increasing complexity, validation and emulation become critical pieces to ensure high quality of the design. Finally, all these designs must converge faster and seamlessly to meet a regular and rapid cadence of cloud server designs. At Ampere, we started with a clean slate and brought together best practices with experienced and innovative teams to build an overall strategy to overcome these challenges. Yesh, what are some of the challenges with large-scale integration?
Well, Mitrajit, as you said, large-scale integration is a critical aspect of cloud-native servers in contributing to higher density compute nodes. Transistor density has been scaling with each technology node, mostly in keeping with Moore's law. The inherent challenge for cloud servers is that based on compute demand and the rapid cadence of products, the large-scale integration and the associated die sizes are increasing at a rate that bumps up against wafer reticle limits. In addition to these reticle limits, large dies result in lower die yields, increasing costs. To keep pace with compute density needs, we have moved to disaggregating a large single monolithic die into several smaller chiplet dies that all get integrated at the package level, making it seamless at the platform level. By disaggregating into chiplets, we can continue increasing the overall chip-level transistor counts by increasing the number of die chiplets, while the individual die areas can be optimized for yield and manufacturability. Disaggregation does push the integration challenges to other areas. Advanced packaging techniques must adapt to efficiently integrating multiple dies. Die-to-die link latency and bandwidth must continue improving while also increasing signal density and reducing power. Manufacturing testing, validation, and firmware has evolved to manage multiple dies in a package.
A lot of areas get affected during disaggregation, but this enables the server processors getting high core density with the latest technology for performance. How does it look on performance with the latest technologies?
Yes. As we are aware, with any compute, performance is a critical metric, and cloud server designs more so are expected to have sizable performance improvements from one product generation to the next. With each shrinking technology node, device-level performance continues to improve at a good pace, but the challenge is the overall design-level performance does not keep pace, mainly due to back-end aligned technologies, meaning wire resources have not scaled at the same rate. This gap continues to grow with smaller technology nodes. Improving design performance starts by going back to the architecture stage to to choose designs that minimize longer interblock communication and routing on performance-critical functions. This then involves planning out logical hierarchies efficiently, working through design partitioning, floor planning, etc. To further optimize for performance, we use selective and highly customized circuits to speed up critical paths. Priority is also given to choosing optimal standard cell library architectures that provide the best power performance trade-off, as well as choosing taller metal stacks, non-default routing for critical nets, wider via stacks, etc. All these techniques help minimize the performance gap and get the best overall design performance.
Nowadays, all high-performance blocks start with physical synthesis that takes into account the floor plan and the wire delays. Even IR-related optimization now starts at the physical synthesis level. Okay, now let's talk about power optimization.
Sure. Power is a critical aspect indeed. Modern cloud server designs focus on power reduction just as critically as performance improvement. With planar technology nodes, there was a huge focus on leakage minimization techniques. With the advent of FinFETs and better gate control, leakage is controlled, but the increase in gate cap leads to higher dynamic power. With the shift in focus to dynamic power reduction, we work with our foundry partners to explore various design technology co-optimization techniques to help reduce area and power. On design side, we start again at the architecture stage by making design trade-offs decisions based on usage scenarios to minimize power. This power optimization further shifts to various circuit and SRAM level microarchitecture optimization techniques working in conjunction with physical design to customize implementation. These customizations are done based on a deep understanding of the specific architecture and usage needs. In addition, there is a focus on advanced power management techniques based on usage scenarios to further optimize power. Beyond compute, I/O interfaces are a big portion of the overall server design power. There is a significant focus on reducing I/O power generation to generation. With that, can you tell us how have the I/O interfaces changed over time?
As server designs are growing in compute, they need more I/O bandwidth. Generation over generation, we are increasing DDR or PCI speeds or both with more channels and links. The industry has done a good job on increasing the line rate over time. In fact, at ISCC, you will see a lot of good papers on high-speed SerDes and memory designs. However, during integration, connecting the large quantities of IOs from the dies to the chip pins to the systems with increased signal integrity requirements is very challenging. At Ampere, we invested in co-design between die, package, and systems from the planning stages down to design release to get this convergence. And we do end-to-end analysis and lot of attention to high-quality routing, components, and materials to achieve the high speeds. Then, as you said, the IOs and the interfaces now take up more area and power. A lot of innovation is now happening in power management with IO traffic. Finally, IO compliance and server quality bit error rate is very hard, and it takes us all the way to the final stages of validation to get it right.
Yes, signal and power integrity compliance is a challenge and requires good upfront planning to get it right. We spoke about everything that we are building and the challenges associated with them. How long does it take for you to build and keep up with the rapid cadence of products?
So design convergence and product design cycle is where all cross-domain teams come together. Keeping up with the server demand the cloud server semiconductor is executing at a rapid pace. At Ampere, our infrastructure is now built to support multiple design stage overlaps, shortening cycle times by planning for silicon success and developing all system collaterals before chip in-house. For post-silicon success, test chip-based IP validation, emulation, firmware, and platform readiness play key roles. In silicon engineering, long runtimes during block convergence, partition convergence, and chip PDV, they stand out.
For sure, as we add new customized circuits, test chip-based validation is critical. With large-scale integration and the growing sizes of design databases, how are tool runtimes scaling, particularly given the rapid cadence of designs?
Generation to generation, the sizes of the blocks increase due to speed, FIFO sizes, bus widths, and added interface. In addition, the lower geometries have more complex rules, and the place and route tools spend a lot of time either legalizing placement or updating delay numbers or fixing metal DRCs. With each new generation, without any optimization, the runtime of key blocks typically increase by about 50%. Now, improvements in tool flows and EDA enhancements typically recover 25%. After that, the common practice is to add more CPUs to further parallelize. Adding more CPUs nowadays give diminishing returns. At Ampere, we add a pre-planning phase, redefining the block sizes and partition sizes to make sure they converge at a reasonable time. At the higher level, we use the tile-based approach and timing abstractions to converge at the subsystem faster. With all these combined techniques, we have managed to keep a constant design convergence with each generation.
Completely agree with the runtimes in advanced nodes. This is true even with SRAM and large circuit blocks. Given this complexity, what are some of the challenges in validation?
In the validation domain, the biggest challenge in today's cloud server design comes in emulation. Emulation is key in achieving a shorter design cycle, enabling performance and validation firmware readiness before chip in-house. However, you get the maximum advantage when the full CPU subsystem and the memory subsystem together can be built in the emulator. The challenge here is that the gate count of these server subsystems increase faster than the emulation capacity, even with the emulator companies doing refreshes regularly. At Ampere, we plan these capacities few years in advance, break the subsystem into quadrants, and invest in modeling the memory subsystems to improve capacity. Emulation is essential in cloud server designs, and we have found so many applications we can run on the emulator. Even after tape-out, the emulation work continues with pre-silicon firmware readiness before the chip in-house. Speaking about silicon, back to Renée.
Thank you, Mitrajit and Yash. And if you do all of that, it results in an 80 or 128 core microprocessor that operates at 3 gigahertz with top-tier performance in less than 250 watts, setting the bar for the future. As you heard from the team, at Ampere, we have really focused on the key design challenges facing the industry as we move forward towards a continued desire for high performance in a low-power world. I'm going to leave you with a final thought. When people talk about innovation in the next decade of semiconductors, what they really mean is design. Design and new techniques are more important than ever as we face the ever-complex and ever-changing challenges in semiconductor manufacturing. So the future is about you. So I want to wish all of you good luck with your designs, and thank you for watching.